Hi students. So let's move to the next topic from electrostatics, and which is called electrical potential due to sphere. Okay, electrical potential due to a sphere means we are going to find out electrical potential for a sphere at various positions, like we have learned in electric charges and electric field chapter. We are finding the electric field intensity inside the sphere, surface of the sphere, outside the sphere. The same concept we are going to apply will be here also, the same logic or the same positions we are going to find it here, but it's not for electric field intensity, it's for electrical potential. Okay, so in with respect to sphere, we have last sessions we have learned some concepts. So let me make it a refreshment for you. So spheres are two types. Okay, one is hollow sphere, one is called the hollow sphere, or this is also called a spherical shell. Spherical shell, which means what? Inside it is empty, nothing. So there are two things will be there, conducting and non-conducting. Okay, so this hollow spherical shell, which is a conducting and non-conducting, conducting and non-conducting, this is one category. Okay, the same category will consist of, we also called this as, this is one category, and the same another category within this part will be equal to a solid sphere. This is solid sphere conducting or conducting solid sphere. So this is actually a same category. This has no difference. This is one category. And another one, this one category means what this indicate, charges are present only at the surface. Charges are not present at inside. So inside it is empty. So if we have seen in question paper with a solid sphere conducting or conducting solid sphere or conducting hollow sphere or conducting spherical shell or non-conducting hollow sphere or non-conducting spherical shell, something like this, if you see, this all together is indicate charges are distributed only at the surface, not at inside. Another point is like non-conducting, this electric charges, electric field also we have learnt. Non-conducting sphere, non-conducting sphere means, or non-conducting solid sphere, non-conducting solids, what this indicate means, charges are present everywhere. So inside it is filled like a iron rod or iron pipe. Okay, inside it is not empty, inside also it is filled with metals. So charges are filled or charges are available everywhere over the surfaces. So that is the induction. So two things we are going to see will be here. One is hollow spherical shell, and or it is also called a conducting solid sphere conducting, or we can also say conducting solid sphere. Both are same, both ways we will write conducting solid sphere. So all are same. Okay, this all together indicate inside it is empty, only charges are present at the surface. It is just like our normal pipe. Okay, inside it is empty, kali, nothing is there. But this is also a kind of pipe, but it is inside it is filled like an iron rod, it is completely filled with the metals. So that is an example of a non-conducting solid sphere. So we'll start with this part. So we have actually two things has to do. We have to find out the electrical potential inside a surface, outside for this category, and we have to find out electrical potential inside a surface, outside for this category, for the second category. So we'll go one by one. Okay, so we will write the first subheading just to give an overview or a refreshment what we have learned in the last chapter. I repeated here again, there is nothing specific or nothing special will be here. So we'll move to the first subheading under the electrical potential due to a sphere. You can write it as, it is a hollow sphere. Okay, or this is also called thin shell. Okay, applicable for what? Conducting and non-conducting sphere, non-conducting and non-conducting sphere. So this is applicable for all this category. Okay, so we are first sessions in case number 1, or in the first subsections, we are going to find out V at outside. So potential at outside we are going to find out. Okay, so we have a sphere like this, and from center the outside distance is r. We are going to find out the potentials value at here, which is called V out. Okay, this is at a distance of r. Okay, now we have to find out the potential at the point here. This point is called V out positions. So how to find out the potential will be here. Potential here, this is a solid sphere, contains the charges are distributed only at the surface. How to find out the potential? Potential at this point is equal to, yeah, tell me the basic definition. Work done to bring a unit positive charge from infinity to this point. That work divided by what charge I am moving. Suppose I have a charge will be here Q. The charge I am bringing from infinity to this point here, I am doing some work. That work divided by this moving charge is called it as potential. The same concept we are applying will be here. So we are moving from where to where? We are moving from infinity to the V out positions. Okay. So this point I am marking as P. So which means I am moving from infinity to P. Infinity to P I am moving. So potential at P minus potential at infinity. Final minus initial is equal to work done from infinity to P divided by the charge Q. That is the definition of this one. Okay, this is the exact definitions, and we also learned the relations between potential difference and electric field intensity, because in the first chapters we already learned electric field intensity at various points. So it is easy to connect. So if you know electric field intensity, you can find out the potential using that relations. So what is this is called? This is nothing but a potential difference. So Vp minus of V infinity will be equal to, what will do? Okay, so here we know it is minus E dot dr. That is a formula for us, right? E dot dr. But here one thing we what can I say? We want to know one thing. What we want to know, what is that thing is like electric field intensity at outside the surface. Okay, because we are at outside potential we are finding, so we want to know outside electric field. Meanwhile, the other important thing is like here we have to use E dot dr or integral E dot dr. So that is important. Here we are using integral E dot dr. Why I will tell you the reasons. Why we are using integration means, if you are moving from infinity to each of this point, what is the value of electric field intensity? Here one negative signs will be here, right? So negative, this is a standard formula. So electric field at outside we are using. So electric field outside will be equal to K into Q divided by R square. If Q is the amount of charge present will be here. KQ divided by R square. Here R is the distance. While moving each of this distance, electric fields are changing continuously. In the last topic I told, there are three things will be there. One is a non-changing things. There we can use direct multiplication. One is some things which are keep on changing with respect to distance or with respect to time. There we'll use integration. Sometimes there is a abrupt changes will be there. That we cannot use integration. Some other mathematical complexities are there. Some other method has to use, that is not in your syllabus. You don't want to worry about. But here electric field's value will be equal to what? KQ divided by R square. So the electric field at outside will be equal to K into Q divided by R square. Here you can say, if you have coming from infinity to this position, infinity means large value of R. So if you are coming from infinity to P means your R is reducing, so electric field is increasing. So each and every millimeter of distances, what will happen? Electric fields are changing. Because of that change, we are using the integrations. We are moving from where to where? Integral infinity to a P distance. P means what point? At a distance of R meter away. At a distance of R meter away. So potential at P, which is also called V out. The potential at P is called V out. Potential at infinity is equal to 0 minus of integral infinity to R. Electric field intensity at the outside, the same formula I have written will be there, KQ divided by R square into dr. Okay, so here distance and electric field. So whenever a charge will be coming, the electrical force will be here, the electric field and dot dr. So electric fields are directing always away from the charge because it is a positive charge, and the distances is always in the same direction. So E dot dr means what should will come? Cos 0 has to come, because electric field vector and dr in the same direction, which means theta will be equal to 0 degree, because positive charges electric field lines are emerges out. Okay, so we have got this relations and we have to integrate this one. So V out is equal to, what are the constant term? KQ is constant, integral R square into dr, integration limit from infinity to small letter r. Okay, small letter r. So small letter r is a distance from here. We have to integrate this one. So we'll integrate V out will be equal to KQ r raised to so integral 1 by r square. So r raised to minus 2 plus 1 divided by minus 2 plus 1, integration limit from infinity to r. So what this come? We already have a minus will be here. This minus and minus become positive. So V out will be equal to KQ into 1 by r. We have to apply the limit from infinity to r. So what is coming? So KQ into 1 by r minus 1 by infinity. What is 1 by infinity? 0. So it is KQ by r. So electrical potential at outside the surface is equal to KQ by r, outside point. Outside point will be equal to KQ divided by r. What is electric field intensity outside? KQ by r square. Here KQ by r. Electric field intensity at an outside point will be equal to VKQ outside. Electric field is KQ by r square. Potential is KQ by r. Hope this is clear to you. Okay. Electric field at outside the surfaces. Next we will see. The second heading. Electric potential at which surface? At surface point. At surface point. At surface. Second point. So here, what is the only difference? Instead of keeping the point P will be here, I am keeping the point P at the surface. P at the surface. So I can say it is surface electric field, surface potential. So what will happen? We are moving from infinity to the point P and Vp and infinity to. Now this distance to the center is capital R. Distance to the center is capital R. So what is the limit of integrations? Instead of small r, now capital R will come. So here R will come, and V out, instead of V out, we will write it as V at surface. So potential at this surface equal to integral minus infinity to r KQ divided by r square into dr into cos 0. Only the difference is like the integrations limits are changing. Here instead of V out, what will come? Throughout what will come? It is coming as V surface. So it is V surface, and we have V surface, and we have V surface, integration limit capital R, integration limit capital R, integration limit capital R. We are substituting the limit, and this is equal to capital R, and which is equal to V out. That's all. Not V out, V surface, sorry, right? V surface. So V surface means only difference is like integration has to, integral limit has to changes from 0 to capital R, from 0 to small letter r. Okay, so this is a potential at the surface. So the formula is KQ divided by capital R. If it is at outside, KQ divided by small letter r. So we'll go to the third heading. What is the third heading? So now we have find out the potential at outside, potential at surface, and we are going to find out what is the potential at inside positions. Okay, so which means the third one, potential, electrical potential at an inside point, Okay, so we have a hollow sphere like what we have seen before. Charges are distributed only at the surface of the sphere, and we are finding the potential at a point, inside the point, from the center at a distance of r meter away. What will happen? So this is at a point P. Okay, so what is the potential will be here? In the previous examples, like we have written, okay, the potential at this point P is equal to work done to bring a unit positive charges from infinity to this point, but here there is a problem. Okay, normally we have writing as infinity to that point means Vp minus V infinity is equal to minus of integral electric field inside dot dr. Okay, from where to where I am moving? Infinity to P. Here we cannot use this formula. There is a problem in case of if you are taking an inside point. Why? Because I will tell you the reasons. Okay, now if you see, you are coming from infinity. What is the potentials will be here? 0. Okay, okay, potential will be here is equal to 0. You are coming here to the surface. You are coming to here to the surface, then you are coming to inside the surfaces. So what will happen means when you are moving from infinity to an inside point, what will happen? The change in electric field will be there, the change in potentials will be there. That change in electric field from infinity to P, it is not like uniform changes, it's an abrupt changes. Why? Because means here in between infinity and the inside point, what is coming will be here, you have a surface will be here. So because of the surface, there is an abrupt changes are happening at the surface. Abrupt changes are happening for the electric field as well as for the potential exactly at the surface point. That's what, if there is an abrupt changes will be there, you cannot use the integrations between infinity and the point P. You cannot use it. Okay, but whenever between infinity to this point, it is one slot. It's just like a one slot, and the changes are with respect to the distance and with respect to the time, which will have some similarities will be there. And between the surface and inside point till the center, this is another slot. This is S1 slot and this is S2 slot. Two slots will be there. So with respect to S1 slot, S2 slot, if you are moving from S2 to S1, there is a certain change will be there because of the charges are distributed at the surface of this one. And because of that, you cannot take Vp minus V infinity. Instead of that, we are taking another 2 points. What are the 2 points we are taking? We are taking surface and inside point. So we are moving from surface to inside. So which means Vp minus V surface will be equal to minus of integral from surface to P. From surface point to P. Surface is at a distance of what R? Capital R. Inside is what? A distance of small r. So surface to P. Okay, so we have to apply the limits, and we know the electric field the electric field intensity. So we are moving from Vp minus Vs. Okay, so Vp minus Vs means we can split this integral into two ways. Okay, so electric field at the, intensity at the surface and electric field intensity at the inside. So I can say that 0 to R is our total integral, but we are moving from to the point P from the point of surface of this one. So how we can say at capital R to a distance of how much distance we are moving? Small letter. So E dot dr. Capital R to E dot R we are moving, and this changes, this electric field will be equal to. So what is this electric field actually? This electric field is equal to inside electric field, right? From capital R to small r means, capital R means the total distance here, small r means this one. So electric field is at inside. So what is the electric field at inside? Will be equal to 0, because there is no charges are available inside the surface. So electric field will be equal to 0. So which means that what? Vp will be equal to Vs. Vp means our inside point. So inside will be equal to surface electric potential. Surface potential is kq divided by r. That's all. This is a concept behind this one. Okay, why we have, instead of taking infinity, why we have taken the surface mean there is an abrupt changes will be there for electric field and potential at the surface. That's why we are not taking an infinite point. Infinity it is 0, and then inside point it has some value, and from surface it has some value. If there is a uniform changes will be there from throughout with respect to distance, with respect to time, then we can use between that two slots we can use integration. Here infinity to surface it is okay, and surface to inside it is okay, but infinity to inside it is not okay, because an abrupt changes are happening on the surface. That's what we are not taking an infinite point, because if there is an abrupt changes, as like I told in the last topic, if there is an abrupt changes will be there, you cannot use integrations as such. There is some limitations are there. So that's why we are using to the point surface and inside point. So we got electric field, sorry, the potential at the surface equal to potential at inside. Okay, so we'll close this one. So we understood electric potential at the inside and electric potential at surface. Okay, so we'll write the things what we have discussed now. So we know the potential at inside will be equal to kq divided by r, potential at surface will be equal to kq divided by r, potential at outside will be equal to kq divided by small letter r. We will plot a graph for this one. Okay, this is a sphere. I just marked this sphere for this one, and we are plotting a graph for this one. This is a potential with respect to distance. We know inside and surface potentials are same. So potentials are same. So up to the surface the potential will be the same. After the surface, when distance are increasing, potential is reducing. So this will be going down like this one. So here this is V in equal to Vs, and this is V out, and which is proportional to 1 by R. So this is your sphere. It is what kind of sphere? This is nothing but your hollow sphere. Okay, so charges are present only at the surface. So the potential is constant inside, then it is reduces. So if you plot only the graph, then look like this one. This is a plot between the potential and the distance. Okay, this is very important. But at the same time, what is the corresponding plot here for electric field intensity? Electric field intensity, what is electric field intensity? 0. At the surface we have a value. So this is a corresponding plot for electric field intensity with respect to distance for a hollow or thin spherical conducting or non-conducting sphere, because electric field inside is 0, only at the surface and only at these corners, but only at the outside surface, but potential is constant throughout inside to the surface. Okay, hope this is clear, and we'll move to the next heading. Okay, next heading means what? Hollow spherical shell conducting or non-conducting we have learned, and as well as this is, you can additionally write here, this heading is also applicable to what is called conducting solid sphere. So conducting conducting solid sphere, conducting solid sphere. This is also an example of a conducting solid sphere. Whatever we have seen, this is also applicable for this one. So I missed to write this one. You can add this conducting solid sphere. Okay, now we'll move to the second heading. Second heading. What is the second heading? Solid. Solid non-conducting sphere. Non-conducting sphere. What is the difference between that with previous one? Here charges are distributed inside, outside, everywhere. So which means it's a sphere. Charges are there everywhere on the surface and on inside, everywhere will be there. So we have to find out the electrical potential at outside, electrical potential at inside, and electrical potential at the surface. So what we'll find? First, I'm interested to find out the electrical potential at inside. Electrical potential at inside at a points of distance of r. Okay. So what we'll do? Here the same procedures will do. This is a point P and this is a surface point. So we are measuring Vp minus of Vs will be equal to minus of integral. Minus of integral. From where to r? Capital R to small letter r. Capital R to small letter r. We are moving from capital R to small letter r distance we are moving. And electric field intensity inside dot dr. Electric fields are always, away from the charges, and the distance vector dr is always away. Okay, so we are moving like this. Our reference point is center. From the center we are calculating like this. So distance is always measuring from the center. So what is the angle between them? So Vp is called what potential? Inside minus V surface kq divided by capital R is equal to integral minus capital R to R. What is the electric field intensity for a solid non-conducting sphere at an inside surface? Remember the value, KQ small r divided by R cube. If you are not remembering, please go back to the notebook and just have a look and come back to here. Into dr into cos of 0. So V in will be in minus KQ divided by capital R. What all things will be constant will be here. Minus KQ divided by R cube is constant. We are integrating capital R to small r. R into dr into cos 0 is 1. Cos 0 is 1. So we'll continue this part will be here. Okay. So V in minus KQ by R is equal to minus KQ by R cube into what is the integral? R square divided by 2, integration limit capital R to small r. So V in is equal to, this KQ by R is taken to right side. So KQ divided by R minus KQ divided by R cube into, we are applying upper limit minus lower limit. So R square by 2 minus R square divided by 2. Okay. So here I am taking one term is constant. What term? KQ divided by R I am taking constant. So what is coming? 1 minus, here what will be there? 1 by R square will be there multiplied with R square by 2 minus R square divided by 2. This will be there, right? 1 by R square by 2. Okay. So let me make this to be clear. KQ divided by R 1 minus. If I am multiplying these two, what is coming? R square divided by 2R minus, and minus become plus and plus 1 by 2. This minus is multiplying inside. So 1 plus 1 by 2 is how much? 3 by 2. So we are writing the formula KQ divided by R into within bracket 1 plus 1 by 2. So 3 by 2 minus R square divided by 2 times of R. Okay, R square divided by 2 times of R square divided by 3 times of R. This can be, hope you can pause the video, you can complete the notebooks. I am going to rub these sides. Okay, so now will be here, we have here. Okay, I am taking R to be outside to make it as a much beautiful arrangement, nothing else. So R square multiplied will be here. So it is 3R by 2 minus R square divided by 2. This is a formula for the potential at an inside position. This is a formula for potential at inside. Next, I am finding will be potential at the center. Potential at the center means what factor will be equal to 0? Small r is a distance from the center. So center means r will be equal to 0. So what is your formula will come? V at center equal to, will substitute KQ divided by r square into 3r by 2 minus 0. So here r and r will be get cancels. KQ divided by, so 3 by 2 r. Correct? 3 by 2 times of KQ divided by R. This is the potential at the center. Potential at the center. So potential at the center 3 KQ divided by 2R. This is important. Potential at the center and electric field at the center also you have to remember. So hope you understood for solid non-conducting sphere. This is just like what we have done the derivations so far. So direct steps. Once you read the derivations, you will never understood. You will never remember that. So for that you have to take a pen and paper and you have to write it 2 to 3 times so that it will be there in your mind. Okay. So you can note down these 3 points. So I am closing here and move to the next area. So now we have find out the potential at inside. So we are going to find out the potential at outside. Okay. So what is potential at outside? Solid non-conducting sphere, potential at inside we have found now, and at the surface we have found now, sorry, at the inside we have found now. So at the outside point means here we are considering a point called P, and this is at a distance of R, and we are bringing from where to where? Infinity to P. So can you tell me Vp minus of V infinity will be equal to minus of integral E dot dr. So you know Vp means V out, infinity is 0. So minus of integral outside means what? Kq divided by r square into dr. You are integrating from where to where? Infinity to r, infinity to small letter r. This already we have done the integration, right? So kq divided by r power minus 2 plus 1 divided by minus 2 plus 1, integration limit infinity to small letter r. What we have done for hollow sphere? What we have done for hollow sphere, the same things will be there. So the potential at outside will be equal to, integrate and apply the limits, you will get kq divided by r. This is the potential at outside. If it is potential V at the surface, so V at the surface, this is also very simple, right? So what is the difference between them? Here Vp, tell me, Vp, we want to find out the potential at the surface position. So potential at the surface position means Vp minus, so what will take? Vs, surface position. So Vp minus of V surface will be equal to an electric field intensity and inside point, electric field intensity at an inside point, and we will integrate. Okay. So from capital R to small letter r, if you are taking, okay, at the surface point, right? At the surface point means what? Vp minus of, at the surface. So now the point is at the surface, which is at a distance of capital R. So Vp minus V infinity at the surface, integration limit minus infinity to capital R. Here it is small r, here it is capital R. We are moving towards the surface. So E, okay, E electric field intensity into dr. Okay, here, so here we are moving from infinity to the surface. So electric field intensity is not at the surface, electric field intensity is still at the outside one, because we are still outside, we are moving towards surface. From infinity to surface, infinity to surface means the electric field is outside. Do not confuse this one. While you are writing at the surface means you have a chance to take, will be here electric field at the surface. No, electric field is still at outside, because we are moving from infinity to surface. So Vp means V surface, V infinity is 0. So minus of integral infinity to r, electric field kq divided by r square into dr. The same steps will be here. Instead of small r, capital R will be there. Will integrate this one and will apply the limit. So what you will get? Kq divided by r. So inside is k, outside it is kq by small r, inside it is kq divided, the surface it is kq divided by capital R. Okay. So three things we have learned: the potential at outside, potential at surface, and potential at inside point. So potential at inside will be little bit mathematical calculations are there, except that potential at outside and potential at surface will be the same. Only difference is the small r changes to capital R. Okay. This is all about the potential due to a sphere, for a hollow sphere, thin spherical shell, conducting and non-conducting, and solid conducting sphere. All are one pool, one category. Say, and this is for potential at a solid non-conducting sphere. Now we will see the graphical representation of this one. So graphical representation of this one. So potential, we are going to find out the potential changes with respect to distance for a solid non-conducting sphere. So heading is not this one. Solid non-conducting, we are still at solid non-conducting sphere. So in case of a solid non-conducting sphere, this is the potential, this is at a distance r. So if you have a sphere will be like this one, then potential at will be here. We know it is 3 by 2 times of kq divided by r. Okay, after that what will happen? We have another formula. Okay, so based on that inside formula, the potential is reduced like this, then it will be going like this. This slope after the surface, this is like this. Whatever we have seen, this is like this. And this is potential at outside is proportional to 1 by r. This is potential at surface. V surface is proportional to 1 by r. This is where potential at the center. This is the potential at the center. So if you are drawing in a very neat way without the sphere, then the plot will be just slanting like this, then this is like this. So this is potential at the center. So this is the potential at center. This is potential at inside. This is potential at surface. This is potential at outside, this area. Okay, so this is a variation of potential with respect to distance. So draw this graph also. This is also important. Okay, we'll see one example questions from this one. Okay, how the questions are coming for your NEET and JEE examinations from this sessions normally. Okay, so we'll see one example. Suppose I have two spheres, two concentric spherical shell, and whose radius is r1 and its radius is r2 and its charges is called q1 and its charges is called q2. Then this is a sphere of 2 points I am marking. So the point number A and point number B. Okay, this is my first example to you from this sessions, example number 1. I want to find out what is the potential at A. So now if you see, potential at A means two spheres will be there, q1 and q2. So I can say potential at A will be equal to potential due to q1 plus potential due to q2. Any number of charges will be there, that many number of potentials are there. So potential due to q1 means this sphere, this is at the surface. So surface means what? kq1 divided by r1 plus. So q2 because of q2, A point is an inside point. So inside point means what is the potential? kq2 divided by r2. So inside potential is constant, kq by r. Now if I finding potential at B. Potential at B means because of q1 and because of q2. So potential at B because of q1. So q1 will be here. And at the point, so with respect to this sphere, this is an outside point. So what is the potential? kq1 divided by, what is the distance towards outside? r2. With respect to this sphere, I am going to find out potential here. For this sphere, this is an outside point. So kq1 divided by small letter r. What is small letter r? r2. And for B means kq. So for this point, if you are finding the potential due to q2, then q2 is a surface point. What is the surface potential? kq2 divided by r2. This is important. This is a previous year asked question. Okay, you might get confused. So potential at inside is equal to potential at surface. Potential at outside, it is different. So VB means potential here we are finding. So because of q1, for q1 it is an outside point. So kq1 by the distance towards that point is r2. That is because of this one. And for at the point B, because of q2, the q2 is a surface point. So what is the potential at surface? kq divided by capital R. Capital R means what will be here? R2. But if you are finding potential at A means for the sphere q1, it is at the surface. So kq by capital R. What is capital R? R1. And for the sphere number B, the point A is an inside point. Inside point, what is the potential? Again kq divided by its radius, capital R. What is its radius? Capital R is R2. Okay, so based on this, the conceptual questions will come, and another way of asking the question is based on the graph. Okay, so potential for a solid non-conducting spheres graph we already plotted, and this graph is important. Okay, so what is the graph we have plotted? Will be like this and like this. This is for potential with respect to distance. I want to take an attentions to in front of you. This is for a solid non-conducting sphere. So in this case, what is the graph we have learned for electric field intensity? Have you remember what is the graph we have learned for electric field intensity? Electric field intensity like this. Okay, here E in proportional to R and here E out proportional to 1 by R square. What is E in formula? Just now I told, right? KQR divided by R cube. This is the E in formula. So always while you are studying with the potential, always go back and remember what you have learned from electric field intensity, because both are connected to each other. Okay, hope you understand this area from the potential due to a hollow thin spherical shell cases and with respect to solid non-conducting sphere cases. Hope you understand the session so far. Okay, so thank you and have a nice rest of the day, and enjoy your studies with physics and as well as with other subjects also. Okay, so thank you. Bye bye.